All right, today we are diving deep. We're stepping onto the stage where quantum reality actually happens. It's called Hilbert space. And look, if you really want to get your head around quantum mechanics, you have to understand the rules of this arena. It's where all the action is.
Okay, so here's our game plan. We're going to start with something familiar, moving from vectors to kets. Then we'll lay down the rules of the space. After that, we'll see how we actually start measuring states. We'll use that to start building with orthogonality, which leads us right into quantum probability. And finally, we'll put it all together in our quantum toolkit.
All right, first up, from vectors to kets. Let's start somewhere comfortable, right? The world of classical vectors. This is going to show us exactly why the weirdness of quantum mechanics forces us to invent a whole new, much more powerful kind of space. You know, we're all pretty comfortable with this, right? A simple vector, just an arrow with a direction and a length and regular old 2D or 3D space. But a quantum state? That's a whole different beast. It's a type of object that has to carry way more information, and it does that using complex numbers, which we call amplitudes. And this is what it looks like. See that symbol? That's called a ket. It comes from this awesome notation that Paul Dirac came up with called bra-ket notation. It's a quantum state vector, and here's the kicker. It doesn't live in our normal everyday space. Nope, it lives in a Hilbert space.
Okay, so section 2, the rules of the space, and specifically defining the inner product. You know, every space has its own set of rules, and a Hilbert space is no exception. We've got to define the one key operation that gives this whole thing its geometric backbone. And that operation is the inner product.
So here's the formal definition, but don't worry, we're going to break it down. At its heart, a Hilbert space is a vector space, but it's built with complex numbers. That means we can add vectors and scale them up or down. But it's got two extra special ingredients. First, an inner product, which is how we get ideas like length and angles. And second, this really important property called completeness. Okay, so this inner product, it's really the engine of the whole thing. The best way to think about it is like a souped-up dot product. You take two vectors, you do the inner product, and out pops a single complex number. And it all runs on three core rules. First, conjugate symmetry. This just means that if you flip the order of the vectors, you get the complex conjugate of the original answer. So order matters. Second is linearity, which just means you can distribute things like you'd expect. And third, positive definiteness. This one's huge. It guarantees that the inner product of a vector with itself is always a positive real number, which is basically its squared length. It can only be 0 if the vector itself is 0. Now, a picture like this really helps make those abstract rules feel a bit more real. What you're seeing here are vectors in C². That's the Hilbert space for a single qubit. And you can see how each of these vectors has a real part, the solid line, and an imaginary part, the dashed line. The inner product is what lets us figure out the geometric relationship, the angle, so to speak, between these weird, complex arrows. All right, moving on. Section 3, measuring states, where we'll talk about norm, distance, and completeness. So now that we have the inner product, we can finally talk about the length, or what mathematicians call the norm, of a quantum state. And this is going to lead us to that final kind of mysterious ingredient from the definition, completeness. This is the secret sauce that makes a Hilbert space a Hilbert space. So what is this completeness thing anyway? And more importantly, why should we, as physicists, even care? It sounds like some abstract math thing, right? But trust me, it has huge, real-world consequences for how we describe quantum systems evolving in time. Completeness is all about making sure things converge properly. So picture a sequence of vectors, and imagine them all getting closer and closer and closer to each other. We call that a Cauchy sequence. Now, in a space that is complete, we have a guarantee. We know for sure that this sequence is heading towards a specific limit point. And, crucially, that limit point is also inside our space. Basically, completeness means there are no holes. There are no missing points for our sequences to converge to. So, why is this no holes idea such a big deal? Well, it means our space is continuous, it's smooth, and that is what lets us use the powerful tools of calculus. Think about it. When we describe how a quantum state evolves, like with the famous Schrödinger equation, we're using derivatives and limits. And for any of that to work, we need to be absolutely sure that the limits we're calculating actually exist inside our space. Completeness is that guarantee. It makes the physics work. Okay, section 4, building with orthogonality, and we're talking orthonormal bases. So we've got our space, it's complete, it has an inner product. Now it's time to build a coordinate system. And in a Hilbert space, our coordinate axes are made from something called an orthonormal basis.
So what exactly is an orthonormal basis? Well, it's just a set of vectors that are all perfectly perpendicular to each other, that's the ortho part, and they all have a length of exactly 1, that's the normal part. This means if you take the inner product of any two different basis vectors, you get 0. And if you take the inner product of any basis vector with itself, you get 1. That little delta symbol, the Kronecker delta, is just a neat way of writing that down. And here's why that's so incredibly powerful. Think about a regular 3D vector. You can always break it down into its x, y, and z components, right? Well, it's the exact same idea here. Any quantum state, no matter how weird, can be written as a combination of these basis vectors. And those coefficients, the little c's in the sum, they're just the amount of projection the state has along each basis vector. And how do we find them? You guessed it, with the inner product. Okay, this is it. Section 5, quantum probability and the Born rule. This is where all the abstract math we've been doing, the geometry, the inner products, the bases, finally connects to the real world, to the actual predictive power of quantum mechanics. It all comes together right here, in the Born rule. This rule is one of the absolute cornerstones of quantum theory. It's super simple, but also incredibly profound. It says that if you have a system in some state, let's call it psi, and you want to know the probability of measuring it to be in a specific basis state, all you have to do is find the projection of your state onto that basis vector and then square its magnitude. That's it. Probability is literally just a geometric calculation. Let's make this concrete with a simple qubit. Its state is some combination of the ket 0 and ket 1 basis states, right? With these complex numbers alpha and beta, telling us how much of each. So if you want to know the probability of measuring this qubit and getting the answer 0, you just take that alpha, find its magnitude, and square it. Simple. And the probability of getting 1? You just do the exact same thing with beta. It's a straight-up translation from the geometry of the state vector to the odds of a measurement. Okay, last section, number 6, the quantum toolkit. Let's put together all the practical tools that physicists and engineers are using every single day. We're talking about the slick notation we've been using, the different sizes of Hilbert spaces, and the math objects that stand in for actual physical measurements. So, this bracket notation from Dirac, it's more than just a cool symbol. It's a crazy powerful shorthand. The ket that we've been talking about, that abstract vector, has a very concrete representation as a column vector. And it has a partner, the bra, which is just a row vector. And guess what? When you put a bra and a ket together to make an inner product, it just becomes simple matrix multiplication. And what's so cool about this whole framework is how flexible it is. You know, for a single qubit, the Hilbert space is tiny, just 2 dimensions, what we call c². But what about a particle that could be anywhere along a line? Well, its state is a wave function, and that thing lives in an infinite dimensional Hilbert space called L². And the rule that all probabilities have to add up to 1, well, that just turns into an integral. So how do we actually represent physical things we can measure, like position or momentum or energy? We use these special mathematical objects called Hermitian operators. Now, what makes an operator Hermitian is that it's equal to its own conjugate transpose. It's a very specific mathematical property, but it has a hugely important physical consequence. It guarantees that whenever you do a measurement, the answer you get is a real number. And that's a good thing, because, our measuring devices don't spit out imaginary numbers. All right, let's wrap this all up. Let's look at the big picture. What have we learned? A quantum state? It's just a vector. The inner product? That's just how we find projections. The norm? That's just length. An orthonormal basis? Those are just our coordinate axes. And the big one, probability? It's just the squared length of a projection. When you boil it all down, it's all geometry. So really, the main takeaway here is pretty simple. If you want to understand the rules of quantum mechanics, what you really need to understand is the geometry of this elegant, abstract space. The physics isn't something separate, it grows right out of the mathematical structure. And that leaves you with a really cool question to think about. What other laws of physics are secretly just geometry in disguise?